Welcome to week 6. This week we're going to be continuing our discussion of oscillations. We're going to pick up where we left off and end up talking about resonance. So remember last time when we left off, we were talking about a mass on a spring that had the spring force acting on it, obviously, and also a drag force that was proportional to the velocity. We had the general differential equation, and I had given you 3 different sets of values for the constants. Well, I set the mass equal to 1 kilogram in each case, but changed the drag coefficient C and the spring constant K. And you had come up with 3 different solutions, and I'll remind you what those were. Alright, so we had these 3 different solutions, and I told you this first one was called overdamping. The second one is called underdamping. And the third one is called critical damping. So remember, you know what exponential decay looks like, and when you see complex exponentials, those correspond to oscillations like sines and cosines. So here's what I want you to do. Okay, so I want you to sketch a graph for each of these solutions, one for overdamping, one for underdamping, and one for critical damping. If you need to use a computer tool to figure out how to plot these, don't worry about the exact numbers, just pick some constants for A and B and see how it looks. And then I want you to describe in words how the object moves. Okay, take a minute and try that out. Okay, so the first one is flat out exponential decay. And what does that mean for our object? It means that the mass, okay, so it's gone to positive x in this particular version. So it's been stretched to the right, and then it just comes quickly back to the resting point at equilibrium. Okay, let's look at the second case when it's underdamped. Okay, so this has an envelope of exponential decay, but it's oscillating. And this is something we see in everyday life all the time. Anytime you have something vibrating and then eventually it stops, this is what it does. So I really like talking about underdamping just because it's what we're accustomed to seeing. Or like if you have a pendulum in your classroom that, there's too much friction in the string you have attaching it to the ceiling, and that'll stop eventually. Or you just have a spring and you stretch it and eventually it stops vibrating. Okay, now critical damping. Critical damping also looks a lot like exponential decay, that the object just comes to rest at the equilibrium point pretty quickly. So if we were to look back at what we saw in each case, so in all cases we kept mass set equal to 1 kilogram for all 3 of them. For our particular numbers, in the case of overdamping, we had a bigger drag coefficient and a smaller spring constant. And then in the case of underdamping, we had a smaller drag coefficient and a bigger spring constant. Well, can we figure out what that mathematical relationship should be where exactly is the border between underdamping and overdamping? The border, and at the border is critical damping. So how do we figure out exactly where that is? Let's go back to our original equation. Alright, so this is our general equation. We solve it by writing a characteristic equation and then solving the quadratic equation for r. I'm singing this to the tune of Pop Goes the Weasel. Okay, so if it is overdamped, meaning you get a purely exponential decay solution, that means that what is inside the square root comes out to be positive. So because then we have the square root of a positive number, we get a real solution. When c squared minus 4mk is positive, real solutions. Underdamping occurs when what's inside the square root is less than 0, because then you're taking the square root of a negative number that gives you an imaginary r that gives you a complex exponential, so you get oscillations. And critical damping, that's when you only get one solution. You only get one root instead of two roots when you're looking for r. So that's when what's inside the square root is equal to 0. If I just rewrite all of these, you get overdamping when the drag coefficient squared is bigger than 4 times the mass times the spring constant. You get underdamping when the square of the drag coefficient is less than 4 times the mass times the spring constant. And you get critical damping when the drag coefficient squared equals 4 times the mass times the spring constant. Now, if you're looking at this in your book, you will see symbols like gamma where they rearrange these constants. And so they have various preferred constants for talking about these things. But this gets you the general idea. Let me know what you think of that. Now I want to move on to talking about resonance. So I remember when I first learned about resonance in high school, my teacher showed us the Tacoma Narrows Bridge collapse. I'd be interested to hear if you all show that video to your students, or if there's some other examples of resonance you like to share with your students. The reading about atomic force microscopes is related to this topic as well. So as it turns out, resonance occurs when you have the situation where you have something that can oscillate and there's a driving force. So maybe that driving force is the wind, maybe that driving force is pushing. But now we have an object where in addition to the drag force, in addition to the spring force, now we also have a driving force. Now I put myself in the unfortunate position where two of my forces would make sense to be called FD. So F drag, but now we also have F driving force. And this one we're going to model in the most algebraically simple way we can get away with. We're just going to write the driving force as F naught times an exponential. And this omega is a frequency. It's the angular frequency, where the angular frequency is 2 pi times the frequency that we often write as letter F, but is also written as the Greek letter nu. I tend to abbreviate frequency with the Greek letter nu rather than the letter F. Okay, now the reason we're doing this is because really our oscillations should be models as sines and cosines, but we know that complex exponentials are the same as sines and cosines. Now the issue here is because I don't have minus I omega t as well, that this is really a complex driving force. Well, that doesn't really correspond to anything in reality, so what we say is that our driving force is actually the real part of this. And this is just the beginning of what seems like some clever trickery. But this happens a lot in physics, is that we'll just use one complex exponential to represent something that should oscillate. I find it easier to deal with in quantum because quantum is hard to conceptualize as something that's real anyway. But this works out. It's experimentally verifiable. But let me know if it bothers you. Okay, so the first thing I want you to do is write out the differential equation of motion for an object that's subject to these three forces. Okay, just write it. Do not attempt to solve it. Alright, pause and give it a go. Alright, so we have MA equals the sum of all of our forces. Now I'm going to rearrange this into a form that's more standard for solving differential equations. Okay, we have not solved this type of differential equation before in this program. We didn't do this type in math methods, and we haven't done it yet this semester. It involves a lot of cleverness. Now, to get you in the right mindset for the method for solving this differential equation, I have a couple exercises for you. All right, so here's what I want you to solve. Here are some hints. Okay, so these i's are the imaginary number, you can set the real parts of the equations equal to each other, and you can set the I parts of the equation equal to each other. You get two separate equations. You can solve for two unknowns. You're going to do the same thing on number 2, but remember to use Euler's formula. You have two unknowns, x and theta, but because you have two equations, it comes out okay. So this is something cool when you write a complex equation that actually is two equations. So try working that out. If you need to see what I mean and I haven't quite been clear, go ahead and push play and then go from there once you kind of see what I mean. Okay, so we write a real equation. X plus 2 equals 4. That's the real parts of the equation. Then we write an equation for the imaginary parts, which is y minus 3 equals 5. So we can solve this. X equals 2 and y equals 8. Now let's set up our equations for number 2. Well, first I'm going to use Euler's formula, which is that the complex exponential equals cosine theta plus I sine theta. Now we can write our real equation, 1 equals cosine theta, and our imaginary equation, x equals sine theta. So we can use the real equation to solve for theta and then plug that into the imaginary equation. So that means theta equals 0, or any multiple of 2 pi, right, because the unit circle repeats every 2 pi. And if we plug that in to sine, well, sine of 0 or 2 pi or 4 pi or 6 pi is 0. So x equals 0. So that was just to get you in the right mindset for some of the tricks involved in solving our differential equation. Let's go back to our differential equation now. Okay, time for a whole lot of cleverness. A lot of ways to solve differential equations look like cleverness, and that bothered me when I was first learning them. But then when you start to see that if you experimentally test them, they work, it kind of builds more faith in the process. Okay, so first bit of cleverness. So we have something that's a spring, and then it's being driven by a driving force that oscillates. Okay, now notice, remember, we chose a driving force that oscillates. It could be just like pushing a child on a spring at regular intervals, which is not exactly a cosine or sine, but we can model it as a cosine or sine. Or it could be wind. So that's what we have. We have a spring being pushed by an oscillating force. So it's a pretty good guess that the motion of our object on our spring is going to be an oscillation as well. So we just guess. Alright, x as a function of time is going to have some amplitude to an oscillation. So we're saying it has the same frequency as our driving force, but we're going to say it's offset by a phase from the driving force. Are you okay with understanding what it means if you just delay the phase? Right, so if you just have sine, it looks something like this, but then if you delay it, it might look something like this. And it could have a range of offsets. It might just be delayed by this much. So that's all determined by the phase. Okay, so we're just guessing our solution will have the same frequency as the driving force, but be delayed by some phase. Now what I want you to do, okay, so I want you to find the derivative of our guessed answer, x of t, with respect to time. I want you to find its second derivative, and then I want you to plug x dot, and x double dot into our differential equation. Take a few minutes and try that out. Okay, so x dot equals the time derivative. Okay, so that brings down the I omega. Leaves us the a. And we keep our exponential. Now when we take the second time derivative, we bring down another I omega. And we leave our a and our exponential. So we end up with I squared is minus 1. Okay, now we want to plug this in. So we get Okay, so here we are. We have that all plugged in. Now we're going to do some cleaning up. Alright, we're going to divide the whole thing by e to the I omega t. This requires you to remember that if you have something like e to the a plus b, that equals e to the a times e to the b. So we're just dividing out the ei to the omega t. So we end up with, now to clean things up a little bit more, I'm just going to multiply the whole thing through by e to the I phi. So that instead of having to write e to the minus I phi 3 times, I only have to write e to the I phi once. Now finally what we need to do is use Euler's formula. But we're running short of room, so I'm going to go to the next page. So I'm just going to copy first the left side of the equation, and then I'm going to substitute cosine phi plus I sine phi for e to the I phi. Okay, now what I want you to do is I want you to take this one equation and write an equation from the real parts and write an equation from the imaginary parts. Okay, pause a minute and do that. Okay, so from the real parts we have, and from the imaginary parts we have. Okay, time to get creative with our algebra. Alright, remember, so what we have is we have our general solution that has a and phi in it. We are looking for a and phi. I think I forgot to say that in the first place. We need to find a and phi. Those are our two unknowns, and we have two equations. So, here's some funny algebra we don't use very often. If we have two equations, say a equals b and c equals d, then it is also true that a divided by c equals b divided by d. So I want you to try that yourself. We have our two equations. I want you to take the imaginary equation and divide it by the real equation. Okay, take a minute and try that out. So we could have divided the real equation by the imaginary equation, but then we would have gotten cotangent, and I wanted to get tangent. So how can we simplify this? Well, the f naughts cancel, and the amplitude cancels. Okay, so what do we get? Alright, to solve for 5, then we get... Alright, so now we have the phase. It looks gross, right? We still need to find the amplitude. Time for another set of clever algebra. Let's go back and say, alright, we have, if we have two equations, then it's also true that you can add the squares of the left side, and that'll equal to the sum of the squares on the right side. Okay, so we have our two equations. So I want you to use this trick on our equations. And when you are trying to clean up, you should come to the point where you have cosine squared plus sine squared. Remember, cosine squared plus sine squared equals 1, so you can clean it up. Alright, try out this trick. This is going to help us find the amplitude. Alright, what a mess, right? Okay, well if we factor out the f naught squared, we get cosine squared phi plus sine squared phi, which equals 1. So we can just simplify the right side to f naught squared. Let's go back to our left side. Well, we have an a in every term. So we have these a's inside the square, so we can pull out an a squared, and then we have, if I change the order on the inside, I get k minus m omega squared. So I'm going to factor out the a entirely, and now I can solve for a. Because a negative amplitude doesn't really mean anything, we don't need to take our plus or minus when we take our square roots. I just realized I dropped a square. I'm going back and fixing that. Okay, so here's our amplitude. We have found it. Oh my goodness, that is a huge mess. Alright, let's write out our solution and all on the next page. So remember, we decided that our solution was an oscillation, but we didn't know what a or phi were, so we solved for those. So the amplitude The amplitude is this mess, and the phase is this mess. This is a mess. Also, it's a complex number, so our real solution should really be the real part of x of t. Or the real part is just cosine from Euler's formula, because a complex exponential is cosine plus I sine, so the cosine is the real part. Okay, so how can we make sense of this? So the resonance, what we all think of as resonance, is contained in this amplitude term. You know, the Tacoma Narrows Bridge collapse happens when the amplitude of the oscillation just gets too big. So, what's going to make this amplitude get really big? So let's look at the amplitude at a couple of different values to get a feel for what it is, and then we'll put the graph together. Alright, so my first question for you. Okay, I want you to find what the amplitude becomes when the frequency of the driving force is the square root of k over m, which we also write as omega naught. That's what we know as the resonant frequency. It's also called the natural frequency, because if we just had this spring, it would oscillate at a frequency of the square root of k over m. It's the driving force that would change it. When our driving force is at that frequency, what happens to our amplitude? Alright, take a minute, plug that in, and see what happens. Alright, let's plug that in. So we have a of the square root of k over m. And here I'm thinking of a as a function of omega, and phi as a function of omega. Okay, so, well, omega squared is k over m. That means these m's cancel, and then you have k minus k, this is 0, so this entire term goes to 0. So we have c squared omega squared square rooted, so that's c, oops, haha, I forgot to plug in k over m right here. So that's c times the square root of k over m. Or you could just write it as f naught over c omega naught. So, when you set the frequency equal to the natural frequency, the square root of k over m, this term goes to 0. Now ask yourself this question: could the amplitude ever be bigger than that? When this term goes to 0, the denominator of the amplitude is the smallest it could ever be, which means the amplitude is the biggest it could ever be. So amplitude is largest at the natural frequency. Okay, now I have a couple more questions for you. To get a feel for more parts of amplitude as a function of frequency, we ask ourselves, what is the amplitude when the frequency equals 0? Well, what does frequency equal 0 even mean? It means you have a constant driving force. You just push and you keep pushing. It never changes. And the other question is, what does the amplitude become as omega goes to infinity? So that's a force that just keeps repeating really fast. And when taking something to infinity, remember, you don't need to be a formal mathematician and take limits. You can be a sloppy physicist. I'm going to go to the next page so I have enough room to write this out. Okay, so the amplitude at 0 is just f naught over k squared square rooted. So it's just f naught over k. And when you take the amplitude at infinity, we have f naught divided by infinity plus infinity. Squares and square roots of infinities are still infinity, and 1 over anything over infinity goes to 0. Alright, let's sketch our entire function. So you could use any old tool to graph this, but I like to just put down the points that I do know and go from there, and negative frequencies don't really mean anything. So, wow. So at omega naught equals the square root of k over m, the amplitude is its maximum. And that maximum value is f naught over c omega naught. And we're plotting amplitude as a function of omega. where it intersects the y-axis, that's f naught over k, and it's just going to 0 out at infinity. So at resonant frequency, at the natural frequency, the amplitudes get very large, but move away from that and the amplitude will drop off relatively quickly. Once you get far enough away, you're not going to get much oscillations at all. It's going to damp down. These are lots of important things to consider in industrial design. If you have any equipment that might vibrate for whatever reason, and you know all sorts of things vibrate, then you're going to need to know over what frequency range you have to worry about any driving forces. In fact, one of my students was telling me about all the design he does in aircraft and how they have to scan their aircraft to find its resonance frequencies so that it doesn't break. I thought that was really cool. So one of the things you have to think about when designing things and when studying resonance is full width half maximum. Let me know if you've heard this term before. It tends to show up a lot when you're in experimental designs. So the half maximum is the maximum value of A divided by 2. And you just want to see what frequencies are at either end. And then you want to find how wide this is. So it's a measure of how sharp the peak is. Now we're not going to go through all of this, but what it comes out to is that full width half maximum for this peak is the drag coefficient divided by the mass. So what we see is that when there's more damping, we get a broader peak. And we know that more damping corresponds to more energy loss. Now there's another quantity called the Q factor, and if you chose to read the article about atomic force microscopes, you probably saw something about this. The Q factor is inversely related to 1 over m. So the peak becomes sharper with a higher Q factor. A higher Q factor means there's less energy loss. And in designing atomic force microscopes, these Q factors matter. Have any of you heard about Q factors before? So these really are things that have to be taken into account when building anything, because whenever you build something, you need to make sure that the resonant frequency isn't something that's going to show up, because then things get dangerous. Just like on the Tacoma Narrows Bridge, and that is a very extreme case. Let me know if you have any other examples of resonance that you'd like to share. So the last thing I want to talk about is what the phase means. So my question for you is, what's the phase at the natural frequency or the resonant frequency? Alright, take a minute, plug that in and see what happens. You may need to look at a graph of inverse tangent if you don't remember what sorts of values that will give you. Okay, so, we're dividing by 0, which means we need to find the inverse tangent of infinity. So if you just look at a plot of inverse tangent as it goes to infinity, you'll see that it goes to pi over 2. So at resonance, the phase delay is pi over 2. So kind of, if you think about something that's swinging along an arc, say you're pushing a kid on a swing, there are certain times when you're pushing a kid on a swing that are not going to do you a lot of good. So you're saying that the phase of the position of the object is pi over 2 out of phase with the driving force. So x of t, okay, and a phase difference of pi over 2 corresponds to switching between sine and cosine. So if x of t is out of phase with the driving force, because velocity is the first derivative of position, cosine switches to sine, that means velocity is in phase with the driving force. So that means the driving force should push with velocity rather than with position. So you want to give the maximum push at the point of maximum velocity. So say you've got a kid on a swing, you'll get the maximum force pushing near the bottom of the swing, pushing forward. And I think that makes sense. So the first thing I think about when I'm pushing my daughter on the swing is that I'm pushing her when, say, she's back here. But then I keep pushing through to here. But then I'm not pushing when she's over here. and I'm not pushing when she's swinging back that way, that definitely doesn't make sense. Let me know if that makes sense to you, or if you have any other examples of how you think you could make sense out of what this phase means. Because maybe there's a better example than thinking about pushing a kid on a swing. Okay, so there's more about this in chapter 3 of your textbook if you want to read more about Q factors. If you want to read more about applications, I would check out the atomic force microscopy article. And I know my student who actually tests everything for when it's going to break definitely has to worry about this. But let me know if you know any applications of resonance. I'd really be interested to hear how you talk about it with your students and what all the real life applications are. There's certainly more we could do, but we're moving on to another topic next week. Let me know if you have any questions. I'll see you next week.